Good morning from NASA's Jet Propulsion Laboratory in Pasadena, California. I'm Jane Platt with the Media Relations Office, and our topic today is LDSD, Low Density Supersonic Decelerator, or as some people like to call it, the Flying Saucer. And in fact, the saucer-shaped vehicle was tested on June 28th in Hawaii on the island of Kauai. And the team has had some time to analyze the data. They're going to share with us today some preliminary results, and they also have some pretty cool high-definition video to show us. I'm going to start out by introducing our panelists. We have from NASA headquarters, Jeff Sheehy, and he is the senior technologist with the Space Technology Mission. We also have Mark Adler from JPL, and he is the LDSD project manager. Also from JPL, Ian Clark, who is the principal investigator for LDSD. We're going to start things off with Jeff.
Well, hi. I'm Jeff Sheehy. I'm the Senior Technical Officer of the Space Technology Mission Directorate. I'm pinch hitting for my boss, Dr. Mike Gazarek, who wanted to be here today but had another issue come up, and so he sent me out here. And I'm really proud and pleased to be sharing the stage with Mark and Ian here. It's been a heck of a summer for space technology. It's been a heck of a summer for these guys. And the flight tests that they conducted, the successful demonstration of the low-density supersonic decelerator technologies has been a centerpiece of a technology campaign that the agency has in progress this summer. A lot of highlights of different technology activities in the agency, including those of Space Technology Mission Directorate. You can see all that stuff at the NASA website. But we've been testing the largest composite cryogenic propellant tank ever built. That was built by Boeing, and it's being tested at Marshall Space Flight Center. We've been testing thrusters for a new green propulsion system built by Aerojet and going to fly on a demonstration led by Ball Aerospace. That'll fly in early 2016. We've done overwhelmingly successful tests of some high-power solar arrays that'll be used in solar electric propulsion systems for asteroid retrieval missions and cargo missions to Mars. So a lot of the focus of the agency, as you can see from the graphic, is developing technologies to facilitate human exploration of Mars, the technology pathway to Mars. It really boils down to you got to get there, you got to land there, you got to live there, and you probably want to return from there. And so these technologies that Mark and Ian have been working on are all about landing on Mars. Landing on Mars is really hard. Just about 2 years ago, the agency and a team from JPL landed the Curiosity rover on Mars, and maybe many remember watching that and seeing the dramatic entry of that and descent through the Martian atmosphere and landing on Mars with a very complicated series of mechanisms to get that rover safely on the surface of Mars. This flight test also had a very complicated series of mechanisms to get the vehicle to the right flight test conditions, and Mark and Ian will tell you all about that. So we're creating new knowledge, we're developing new capabilities, we're demonstrating new technologies. That's what we're all about in the Space Technology Mission Directorate at NASA. And this project has been doing all of those things in a very big way. And you'll see that as these guys talk. So again, I'm just glad to be here, glad to be sitting next to these guys. I first met these guys about 4 years ago when they were just starting out on this project. And I remember going into a review at JPL, dressed about like this, I think, and everyone else was dressed about like that, I think. And I remember thinking, yeah, JPL is kind of a different sort of NASA center. But JPL is a NASA center that really gets things done, and you'll see that today. So thank you for coming. I'm going to turn it over to Mark here, but I really appreciate everyone being here. I'm excited to see some of the results that these guys have gleaned from this really successful flight test. Thank you.
All right, thanks, Jeff. So good morning. We're going to talk about what we did this summer. We're going to show you some home movies. We're really happy. We have tons and tons of data, as Jane said. We've been analyzing the data. Nothing makes us happier than data. And a lot of our data we're going to show you is in the form of videos. If a picture is worth 1,000 words, then a video is worth about 1,000,000. And so these are incredible data that you're going to see, and it's really given us great insights, and Ian's going to talk more about those insights. So let's start with some videos of what happened on the mission. This is the night before, on June 27th. We had to come out the night before to get the vehicle set up, bring it up on the tower. Here it is being hoisted up on the launch tower. This tower is used for the balloon to pull the vehicle off. The next morning, we were inflating the balloon with the helium. This is a 34 million cubic foot balloon that's able to carry a 7,000-pound payload to 120,000 feet. There, the balloon, the tip end of the balloon is about filled with helium, and that's just held in that tip end, but when the balloon fills up at altitude, then you'll see it's quite a bit larger. Go to the next video. And so we're just waiting for the video here. Please stand by. So now the balloon is being released from the spool, and we have the balloon going up. The balloon actually extends all the way down to that middle orange thing. That's the parachute. The vehicle comes off the tower. It's now being hoisted entirely by the balloon. It's going up at about 1,100, 1,200 feet per minute up into the sky, going up very quickly. This is an infrared view of the payload going up on the balloon. Here it's a time-lapse video showing the balloon expanding. As it goes higher and higher in altitude, the balloon expands to larger and larger size until it finally gets to this full size that you see right here at 34 million cubic feet up at full altitude. All right, next video. So once we got to altitude, got to float about 2 hours later, we then dropped the vehicle from the balloon. Here you see the vehicle come drop off, and the first thing we'll do is fire up those two spin motors you see right there to spin it up to about 50 RPM. Then this large solid rocket motor fires, the Star 48 motor. It fired for 71 seconds to accelerate the vehicle from 0 to Mach 4, Mach 4.3 actually, in that 71 seconds. Then we fire the spin down motors. The thing comes to a dead stop and then flies very stably at Mach 4, so we're very happy about this. At this point, we've actually achieved most of the objectives of the flight that we had this summer. Our main objective was to show that we could get this vehicle to altitude, that we get it to the conditions that the technologies will see when they actually fly at Mars. So we had to get up to 190,000 feet, which is where this test vehicle ended up at Mach 4.3. And at 190,000 feet, we have about the density of the Martian atmosphere. So that allows us to test the vehicle at the right density, test the technologies at the right density, and test them at the right Mach number. And so now Ian's going to talk about the tests that we actually did. So we had a great flight. We showed the vehicle can do what it can do. And now Ian's going to talk about what we got out of the information from the technology demos.
So as Mark mentioned, the vehicle did an amazing job of getting us to the right speed and altitude, test conditions that would be analogous to the conditions these technologies would see as they would one day be used on Mars. We've been developing a number of technologies as part of this project, technologies that will enable us to land payloads significantly larger than the Curiosity rover, land them to places on Mars that we've never been able to get to before, and land them more accurately. The first of these technologies is something we call a supersonic inflatable aerodynamic decelerator, or SIAD for short. And so let's just go straight to video one of that. So the first video you see here is the camera lens deploying, and this is real-time video of the SIAD inflating very quickly and in a fraction of a second. I think we'll have another view here in just a moment. The SIAD goes from a very tightly packed stowed configuration to a fully deployed configuration in about 0.3 seconds. We even have a high-speed panoramic selfie of the SIAD inflating on the periphery of the vehicle. Look for this on Instagram maybe a little bit later. So from this video and from some of the data, we got an understanding of how well the SIAD performed, and all indications are it did phenomenal. It inflated very quickly in a uniform manner, and it did so without disturbing the motion of the vehicle. I think you saw in the video how stable the vehicle was after the SIAD deployed. This is something that's going to be very important as we consider using these devices at Mars. Another one of the thoughts we had was, as an inflated structure, we were very concerned about how rigid the device would be. Is it going to hold its shape the way that we need to as it's flying through the atmosphere at over 3,000 miles an hour? We got to take measurements of how much distortion we saw, and the early indication are that we saw measurement deflections on the order of about 1/8 of an inch, which for a 20-foot diameter inflated structure is pretty phenomenal, pretty remarkable that we're able to get that degree of rigidity using only a few pounds per square inch, about 3 psi, as we fly through the atmosphere. We were also able to measure the aerodynamics of the SIAD, the drag and stability, and all indications are that the aerodynamics were as expected, or in some cases considerably better than expected from what we thought we would see. All very favorable results for as we look towards using these devices on Mars. And we even got to explore another aspect, which is how much pressure do you really need in this device to have it hold a rigid shape? And we did that sort of in a new way. Remind you that the SIAD is inflated only to about 3 pounds per square inch. Well, atmospheric pressure here at sea level is about 15 pounds per square inch. And so as the SIAD is descending down through the atmosphere, the pressure in the atmosphere begins building up, and eventually it will overcome the 3 psi that we have inside it. And the SIAD will begin collapsing. And so if you go to video 2, you actually see the SIAD in a deflated state beginning to move around a little bit. And so we can go back and see at what altitude and what pressure did the SIAD begin deflating and get a better appreciation for how much pressure is going to be required, particularly as, again, we use these devices at Mars. Another one of the phenomenal successes associated with this flight was the performance of a device we had, a supersonic balloon. It's an inflatable drag device that we developed to help deploy our supersonic parachute, and prior to this flight was certainly one of the riskiest elements of the entire flight. The fears of the balloon not inflating and visions were things that dominated my sleep in the weeks preceding the test. And so if we go to video 3, we have a high-speed uplook video of that balloon. The balloon is packed very tightly into density, the amount of oak wood, and it's shot out the back of the vehicle at 200 feet per second. The vehicle is going 2,500 miles an hour, and you see how quickly the balloon inflates. About 0.2 to 0.3 seconds. The balloon goes from the density of wood to a fully inflated size, about the size of a small SUV. Very successful. You see some motion of the balloon. That's actually motion of the vehicle. The balloon itself was rock solid stable in the wake of this 20-foot diameter vehicle that's punching a hole through the atmosphere at 2,500 miles an hour. All of the performance that we saw from the balloon, the drag and the stability, was much better than expected, and it meant that we could use the balloon to deliver the parachute to the conditions we needed to. So if we go to the 4th video, we see the beginning of the supersonic parachute inflation. So the balloon is pulling the packed parachute off the back of the vehicle. It's deploying all of the ropes and rigging necessary to support the parachute as it's attached to the vehicle. Again, the vehicle is going about 2,500 miles an hour, and we see the parachute beginning to inflate. This is all high-speed, slow motion here. But very early on, it begins developing tears, and once it has those tears, the parachute structure just won't hold its geometry very well. We've learned a lot from this video already. We've learned, for one, that we have more to learn about supersonic parachute inflation. The idea of taking 200 pounds of Kevlar and nylon and deploying it at 2,500 miles an hour, 200 pounds that inflated would be the size of a small warehouse, is certainly a challenging endeavor. There's a lot of physics to this problem that we're now gaining new insights into that we've never had before, and we're learning more about what it takes to build parachutes of this size that can be safely deployed at those conditions. And we're going to take all of that knowledge and feed it towards our flights for next year. So with that, I'll hand it back to Mark.
Thanks. So I'll show you a little bit what happened after that flight and after the experiment portion of the flight. So we can show the first video. Before that, we actually got some really interesting views during the powered flight of the balloon. We had just been dropped from the balloon, as you recall, and you see the balloon coming around in the view there. There it shows once and again. And so we really liked getting these views of our launch system, and it allowed us to see exactly how that balloon performed and how the balloon broke up after the flight. The balloon performed fantastic. We can show the next picture. This is a picture of the balloon itself, if we can get it. There's the balloon, so you can see the fully inflated balloon just after we had been dropped from it. The balloon performed great. We're very happy with it. It's provided by and its operation provided by the Columbia Scientific Balloon Facility out of Palestine, Texas, and we're very, hoping to work with them again next year to launch 2 more of these. So fantastic job, and I'd like to thank those guys. Next video, next picture. So this is actually underwater. So of course the vehicle, once it finished its flight, impacted the water about half an hour later, and this is that parachute underwater. It looks like a big jellyfish, and so we had to bring that out of the water. Next picture. This is our test vehicle floating on the water. It was designed to float. The core structure actually has foam core in it so that even if the vehicle fills with water, it will float so that we can recover it. So this is our supersonic space boat floating out there in the middle of the Pacific Ocean. We have our two EOD guys. These are explosive ordnance disposal guys from the Navy. They are divers that helped us bring the vehicle back, a fantastic team of guys from the Navy that helped with that. And they were sitting on there waiting for the large boat to come along with a crane to get the vehicle out of the water. So next slide. We have, in fact, this is the large boat, the Kahana, with the crane, pulling the vehicle up out of the water and bringing it onto the boat. We didn't have an aircraft carrier, but we had this great cargo boat, which helped us get the vehicle back to shore where we were able to get the data. So a lot of this video you saw, in fact, almost all the video you saw, and the data that we got from the vehicle, we got by bringing the vehicle back and pulling cards and memory cards and stuff off the vehicle. So it was very important for us to recover the vehicle and get all that data back. And the recovery guys did a great job as well. Next slide. We also brought the parachute back. As you saw the big jellyfish in the water, we got that out of the water and brought it onto the boat. In addition to the videos, the examination of the physical parachute itself was very important in understanding what happened in its flight, how it behaved, and what happened during the portion of the flight where it initially deployed and started to come apart. So next slide. So now we're very happy that we got all that data. We've now had a very successful shakeout flight. We've shown the vehicle can do what it needs to do. It's able to get the technologies to conditions. It's able to collect all the data. It's able to get all the imagery. We're able to reconstruct the trajectory, know everything we need to know about these technologies. So next year we're going to really test them. We have 2 flights scheduled for next summer in the June, July, August timeframe. We're going to be flying again 2 more SIADs and 2 parachutes, redesigned, rebuilt parachutes based on what we learned from this first flight. And right here we see the first of the 2 core structures that have been delivered to our JPL high bay. We're going to be doing integration and test starting on this vehicle very soon. We'll get a second one delivered in a couple months and start integration and test on that. And we'll be back in Kauai next summer to do some more tests. So with that, I think, Jane, we can turn it over to questions.
And I do want to mention that these visuals will be replayed immediately after this broadcast, and the entire show also will be archived at www.ustream.tv/NASA-JPL2. All right, we're going to take some questions, as Mark said, and we do have some also from social media. In fact, let's take our first question from Twitter, and the question is, how long was this project in the works before fruition, and whose ideas were they?
Okay, so let's see. The project started in September of 2010. That was when we first got initial funds to start studying the concept and see what we should do, what we could do, what would be the most valuable thing to do. We were in formulation for a couple of years to understand what were the best technologies to test. We got confirmation in December of 2012. This is when we really got fired up with the implementation, started putting together, buying the hardware, putting together the hardware, getting it all built up. So it took us a good year and a half to get to the point where we could actually conduct the flight with the systems we put together. In terms of whose idea was, actually it started with the chief technologist at NASA, Bobby Braun at the time, who felt this would be a good initial project for the Space Technology Mission Director at the time, called the Space Technology Program. And they started, I think it was 8 or 9 projects at that time, and LDSD was one of them, as their initial foray to get data. As Jeff said, we're starting to get data now, starting to come to fruition, starting to see results from all of these projects, and LDSD was one of them. I don't know, Ian, if you have any more on the origins of the project.
Well, certainly the origins of supersonic inflatable decelerators go back to, as soon as we started sending things into space, we started trying to figure out how to bring them back safely. One of the early concepts were inflatable drag devices, and so those go back to the 1960s. Supersonic parachutes themselves even go back to the 1960s. The specific incarnation of the inflatable drag devices that we were testing were really things developed more recently here at JPL and across NASA with the LDSD team. So I'd say there's a long history, decades of this kind of stuff, but certainly the ones that we were testing are more recent in nature.
All right, thank you. And we have a question on the phone, and I should mention for those reporters who are listening in on the phone, if you do have a question, press *1 and the operator will get you in the queue so we can call on you. And if any of the media here at JPL have a question, just raise your hand and we'll try to get a mic over to you quickly and you can ask your question. In the meantime, we're going to take a question from Julia Rosen of the LA Times, and she's on the phone. Hi, Julia.
Hello. First, I just wanted to say congratulations on the successful test. And I was curious if, given the success of the smaller SIAD, if this means that it's likely you'll be able to test the larger SIAD next year during your planned experiments.
Okay, so our current plans right now are to test the smaller side again twice more with the large parachute. This is important mainly for the parachute to give the right conditions for the parachute. We hope to have opportunities later to test the larger SIAD. We are going to be doing, we expect rocket sled testing on the ground of the larger SIAD this coming year so that we can see how the device operates and make sure that it has the proper strength characteristics. And if you have anything more on the large SIAD.
No, I mean, certainly the success of the smaller SIAD has started to ask questions about how do we grow the size of this particular configuration, or how do we mature larger SIADs like the one that we'll be doing the rocket sled testing on. So those are all things that we'll be looking at in the coming months.
All right, we're going to take our next question also from the phone lines. Alan Boyle with NBC. Hi, Alan.
Hi, thank you. I think this is a question for Ian. You were talking about the lessons learned about the parachute. Could you provide any more details about how you avoid that sort of tear and what sort of options you're looking at for the next generation parachute?
Sure. When we built this parachute, we were really designing a parachute that we were optimizing for drag and stability in subsonic steady-state descent. What we didn't have was a lot of insight into the nature of supersonic parachute inflation and some of the physics that governed it. What we saw from this test was that the shape of the parachute is extremely important. The shape of the parachute we don't think was particularly robust to a lot of these intermediate states that you can have as the parachute's inflating at 2,500 miles an hour. We are going to change the shape. We're going to add some structural skeletal reinforcements to make it stronger in areas that we think it's particularly sensitive to. And we're going to improve the deployment of the parachute, trying to present it in as clean a manner as we can, again, in this very turbulent, very fast, dynamic airflow.
Okay, our next question from the phone lines is Miriam Kramer at space.com.
Hi, thanks so much. I actually had a similar question to Alan, so I guess sort of a follow-up on that. So what shapes are you looking at to make it a little bit more stable along with those structural reinforcements?
Yep. The shape modifications are aimed at making it more robust to some of the inflation transients that it sees. The shape that we had you essentially take a very curved parachute, but we had flattened the top of it. What happens with a very flat structure, a parachute by nature is sort of a pressure vessel. Pressure vessels, you don't see too many box-shaped pressure tanks, for example. They like to be curved. And so we're going to go back to including more curvature in regions of the parachute that would be susceptible to some of these high stresses.
Okay, we have a question here at JPL in the back row.
Yeah, following up on the parachute, Robert Lugane with ABC7. Forgive my ignorance here, but if I remember correctly, it won't fully work without one or the other, right? The parachute has to work in conjunction with the inflatable.
Right. In order to get the full benefit, in order to be able to land very large payloads, you need both the SIAD and the parachute. The SIAD helps slow the vehicle down further and get it to conditions that you can deploy the parachute. But you need a large parachute to slow that even further down and get it to the point where you can use something like a sky crane, like what MSL used a few years ago. So we do want to mature both technologies. We've been able to mature the SIAD a year ahead of schedule, and we got to test the parachute and learn from the parachute, and now we get to apply those lessons learned for our flights next year.
I think you just answered my next question, which is how you would define this still as a successful gathering of information despite the failure of the parachute.
Oh, absolutely. I mean, this flight was really just a shakeout flight. We got to put the technologies on this vehicle a year ahead of schedule and see how they performed. The SIAD performed amazing, phenomenal from all the data. And we can now say that it's a device that's mature enough to be used at Mars. We got early data on the parachute, and then we can apply that data to the real tests, which will be next year.
Okay, we have a question now from a student via social media. What gas does LDSD use to inflate itself?
We use two different kinds of gas. One of them is just a cold nitrogen, compressed nitrogen that we use to begin inflating the SIAD. We actually use commercial off-the-shelf automotive gas generators, like the ones that sit behind your steering wheel and help inflate the airbags. The first round of those are just compressed nitrogen, helping get some of the first initial pressure and push the SIAD out to the free stream, and then we just use those gas generators. So I'm not sure about the exact composition of the gas, but it's something identical to what would be used to inflate the airbag in your car.
Okay, do we have any more questions here at JPL? Well, I think that is going to wrap things up for today then. The visuals will be, oh, I'm sorry, we do have a Twitter question.
We do. We actually have one Twitter question and we have two from our Ustream chat. So first up, from Twitter, Carlos asks, have different SIAD configurations been looked into like large petals instead of a single large ring?
Mm-hmm. Before we came up with this particular configuration, there's a number of configurations that have been proposed, again, over the past 4 or 5 decades. We chose one that was initially one that we thought would be a good first step in developing inflatable technologies. Some of these other configurations, deployable petals, those are things also being looked at NASA for different applications, maybe deploying them at the top of the atmosphere before you actually enter the vehicle. Those sorts of concepts are certainly out there, and folks are looking at them. But for inflatable decelerator, the configuration we picked was a logical first step.
Going to our Ustream chat, Luis asks, would it be useful to place a viable payload to be able, let's move on to M. Harris. Could the researchers speak to other potential applications of the parachute?
Certainly. I mean, we use parachutes all the time. And parachutes are a mainstay of our planetary exploration missions. Any environment that has an atmosphere is likely to see parachute because you want to slow the vehicle down as it enters that atmosphere. So parachutes the size of the one we're testing are not dissimilar from the parachutes that we use for the Orion capsule or that we used for the Apollo capsule. Deploying them at the conditions we deploy is something unique, and the challenges we face are somewhat unique to Mars exploration in particular. But that doesn't mean that you couldn't find applications outside of Mars elsewhere in the solar system.
Okay, and our last that I'm seeing here in the chat, do you have any other missions lined up that will use the SIAD?
Our project has 2 more flights of the SIAD next year, at least 2 more flights, hopefully. In terms of missions that will be utilizing the SIAD, we look, on the horizon towards a number of different concepts for missions to Mars. Maybe Mark or Jeff can talk a little bit more about some of those.
Well, wherever we want to land more mass on Mars, if you've seen it, our rovers have gotten very large over time. We started with the Sojourner rovers, maybe like, this big size of a microwave oven. We went to a Mars exploration rover like a golf cart, and then we go to Curiosity. The thing is the size of a Mini Cooper. We're going to keep getting bigger and bigger, and so that's exactly what these things are for. The SIAD, the large parachute, is to land larger payloads on Mars. We expect our payloads to get larger as we go into the future. There will be missions that to put larger rovers on Mars to do more in situ investigation, missions to potentially go collect rocks, missions to try and launch them from the surface of Mars. And so those are going to require larger and larger vehicles. Eventually we want to get to be able to, as Jeff was talking about, land people on Mars. We're going to want to put 2-story condominiums on the surface of Mars. And that gets really big and really hard. And so really this is like the second step of a 12-step program to get to the point where we can put very, very large things on Mars. So there's a lot of things we're going to have to do between now and when we put people on Mars, and we're just getting started now with these kinds of technologies.
All right. Thank you very much. I think that wraps it up for our Q&A, and I want to thank our panelists. And a couple of reminders that you can join the conversation about LDSD on social media using the hashtag 321TechOff and hashtag LDSD. And in addition, the visuals will be replayed here, and they also will be online at www.nasa.gov/LDSD. And the replay, again, will be on NASA TV as well as on www.ustream.tv. And a reminder that we'll be back, I guess, next summer for another test, so we'll keep you posted on that for 2 more tests as we gear up for that, and there'll be some updates before then for sure. Thanks, everybody, for joining us, and have a great day.
actual T0. Copy that.
Oh, Dave Gregory, the balloon looks excellent right now.
Four, 3, 2, 1, drop. Spin up. Stick goes away. TV drop. Check 271. Mach 4. Mach 4. Burnout detected. Spin down. Spin down begun. Spin down confirmed. Velocity 1 detected. Velocity 1 detected. Science inflation. Science inflated.